Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 3.2.3, which is expanding the trig table. Now, before I begin this lesson, I do want to let you guys know that you will need the 3.2.3 resource page in front of you to understand what's going on. You'll find that in your Canvas pages. Without that, you're not going to know where certain numbers are going to come from, but I will tell you where I got them from in the midst of the lesson, but make sure you guys are keeping up with that. That way you guys know where those numbers are at. So it says, first off, on 3-89, it says to, on your paper, draw a slope triangle with a slope angle of 45 degrees. We can go ahead and do that real quick. It doesn't have to be perfect, but I think that this is pretty much 45 degrees right here. And as long as you can just kind of understand where the problem is going, I think that'll be good enough. It says, now visualize what will happen if we increase the slope angle to 55 degrees, which would be longer, delta y or delta x. Explain your reasoning. Well, remember, delta y is the change in y, so that's the verticality of the triangle. Delta x is the lateralness of the triangle. So if I increase this slope angle to 45 degrees, this white bubble actually gets larger. It gets 10 degrees larger right here, and this blue bubble becomes the new 55 degrees, which will then become this guy. Now, if all other parts stay the same, then definitely the only thing that gets longer is the delta y part. Delta y gets longer, right? Because the slope angle is steeper. Let's go ahead and write that in our notes here before we move on. The delta y gets longer because the slope angle creates a steeper slope. And that's it, right? And so imagine going up a hill that's 45 degrees versus going up a hill that's 55 degrees on a bicycle. It would take a lot more work for that 55 degree hill to get over. So now, here's where the resource page comes in. It says using the E tool or the resource page, which should be in front of you. The resource page for 323 is going to be a trig table with a bunch of different ratios that connect slope to degrees of angle measure. And so it says create a right triangle with a slope measuring 55 degrees, then use the resulting slope ratio to solve for x of the triangle at right. So what I'm going to do is I'm going to give you guys what that triangle needs to look like. The right triangle created when a slope angle is 55 degrees, and of course it's not drawn to scale, the slope angle is going to be 10 over 7. And again, I got that from the resource page. So look at your resource pages and we will get that from there. So what I'm going to do now is I'm going to go ahead and compare that to the triangle given. The triangle given has a 55 degree slope angle just like ours and a height of 8 and a length of x. Now from here, the first thing we need to know is that these triangles are similar, right? They're similar by angle, right? The 55 degree angle and the 90 degree angle. Why did we study similarity in so much depth and scale factor in so much depth a short time ago? It's because now I can solve for the delta x of the unknown triangle. So I can say 10 over 8 is equal to 7 over x. I can reduce this dude to 5 over 4 equals 7 over x. That makes the problem a lot easier to manage. 5x equals 28. Divide by 5, and x is equal to 28 over 5. So again, what did I do? I used my known slope angle for 55 degrees with that triangle with a rise of 10 and a run of 7, and I compared it to the triangle given, and I just used similar triangles to figure out the value of x. So 10 over 8 is equal to 7 over x. That's how I was able to do number 3-89. Let's reconnect for 3-90. I'll be back. Moving on to 3-90, it says copy each of the following triangles onto your paper. Decide whether or not the given measurements are possible. And it says if the triangle is possible, determine the value of x, y, or theta. Use the 3-90 student E tool to determine appropriate slope angles or ratios needed. If the technology is not available, which in this case is not, we can use the 3.2.3 resource page. Again, that trig table that we are expanding right now. Round angle measures to the nearest degree, and if it's not possible, explain why not. Okay, let's do it. So again, resource page should be right in front of you for this one because I'm going to pull some numbers out of thin air, and you need to know where those came from. They're going to come from that resource page. So in triangle A, I've got a 70-degree slope angle and a rise of y and a run of 10. Well, if I look at 70 degrees on my resource page, that gives me a rise over run of 13.737 over 5, which if I take a calculator and divide it, that gets me 2.747. So what I'm going to do is I'm going to go ahead and use this slope angle, or this slope ratio, as my comparison for the similar triangle here. So I'll go ahead and say that y over 10 is equal to 2.747 over 1. All I did was I literally reduced this fraction. So now if I cross multiply, I'm going to get y equals 27.47. And there you go. That's the length of y. Again, we're just doing similar triangles here. Now we're just trying to figure out what the degree angle of inclination is going to give us in terms of change in y over change in x. So b, so again, I can say 50 over 6. If I reduce him, because they both divide into 2, that's 23 over 3. Well, if I look back at the resource page, again, I keep referring back to that resource page from 3.2.3, the slope ratio of 23 over 3 produces an angle of 83 degrees. Again, I'm not just, I didn't just come up with that. The resource page gave it to me, and we got that from measuring out these angles exactly. So C, again, we're looking for an angle here, right? We're looking for an angle. Theta is the angle. So now it tells me, again, I'm going to use that resource page. 10 over 1 gets me an 84 degree angle. All right, let me come back with the next ones. All right, let's take a look at this 8-degree slope angle here. So again, I'm going to go back to that resource page, and I'm going to say, well, what is my 8-degree angle? Well, my 8-degree angle gives me 0.141 as my ratio. So again, what that is, that's really the rise over the run of that particular triangle. I'm going to equate him to the rise over the run of this particular triangle. And again, it's just similar triangles, right? So 20 is equal to 0.141x. So if I divide by 0.141, whoops, I get x equals 142.86. And that's how much the run is. Again, I'm just comparing these things to the resource page values here. Well, from here, this one actually should be pretty easy. Because in this case, if there is no rise and there's all run, then technically this angle right here, this angle can't even exist, right? If there's a rise of 0, it's just flat, which means theta has to equal 0 in this case. Hopefully that makes sense. Again, remember, if this thing is 0, this thing is going to go flat. Let's take a look at the 89. So 89 degrees, according to the resource page, is 57.29. And again, I'll put that over 1. That's my rise, or that's my delta y over delta x, right? That's my ratio. So what I'll do is I'll just compare triangles, right? Y over 2, self to self, is equal to 57.29 over 1. Cross multiply, y equals 114.58. And the last one is kind of an odd one, where basically if you have a 90-degree angle here and a 90-degree angle here, this triangle isn't even possible, right? I mean, the triangle is not possible. Because what you would have is you'd have a triangle that has over 180 degrees in it, and as we saw from the triangle angle sum theorem, that just isn't the case. So this one's actually no solution. All right, that wraps up this section here. Problem 3-91 is to fill out the rest of the trig table. So your teachers will have you do that. Otherwise, as always, please leave questions or comments in the comments area, and I will see you all in the next episode.